don't use the mouse.
You don't use the mouse?
I don't use the mouse.
Well, I think you have to.
Oh, just this. Okay, just the
Okay.
keyboard.
Okay. So this is the last talk of the evolution and comparative genomics session, and we started out talking about sets of trees that show hybridization or horizontal transfer relationships, and we're going to return to that theme in the last talk, which is going to be presented by Yufeng Wu, who's from the University of Connecticut.
Okay, so this talk is about on a high-level subject, which is very similar to the first talk. And I'm going to present some work on computing the closed lower and upper bounds for the minimum reticulation for multiple phylogenetic trees. All right, so in case you missed part of the first talk, so let me reintroduce the concept of the so-called phylogenetic network, or I call it Reticulate Network. So normally we try to build a phylogeny by taking the
diagnosis Stevens-Johnson syndrome or toxic epidermal necrolysis. I didn't put up a picture because it's the only ones I was able to find are too disturbing. We're talking about rash from 10 to 100% of your skin, so you can get the picture without
reticulation for 2 trees. So and for more than 2 trees, and we don't have a good method, and sometimes there's in literature there maybe one can impose additional topological constraints, and or you can work with other kind of models like what Stephen just described. In this paper, I will describe the approach that is going to based on trees. In other words, I will insist each of the tree topology is displayed in the network. All right. So I will work on the tree model. All right. So as I said, it's, nobody knows a good approach to compute the exact minimum for more than two gene trees. So how can we? What I'm going to present here is I'm going to ask a slightly different question. In this idea, instead of computing the exact minimum by developing method, as always going to compute the exact minimum. As I said, we don't know how, and I will ask a different question. I will try to give bounds on the minimum reticulation. So in this case, let's look at here. The R mean is the minimum reticulation for the set of gene trees represented as G here. So R mean is as I said, is challenging to compute for the 3 or more trees. And so I said I want to develop bounds. So one bound is a lower bound. I call the RH bound. RH bound is a lower bound, and this is a first such a non-trivial lower bound is known. And for the on the other hand, I also have the upper bound, which I call the seed bound. And the seed bound is work for any number of trees. So why do we want these bounds? So 2 things. First, those bounds provides information on the range of the solutions, even we do not know the exact minimum. And moreover, if these 2 bounds, this is the lower bound, the upper bound, the matches, we actually already know the exact minimum, which is precisely equal to the 2 bounds when the 2 bounds matches. All right. So these are the motivation why I want to do this. So let me give you sketch some ideas about how we can find the bounds, a lower bound in this case, on a given set of trees. And in this work, I will rely on the concept of pairwise distance. So what is a pairwise distance? Pairwise reticulation distance of 2 trees, consider 2 trees, is equal to the minimum reticulation number in any network for these 2 trees, T1, T2. And as I said, there's a practical method. Even it's an NP-complete problem, but there is a practical method that can compute this number. And suppose we have these 3 trees, T1, T2, and T3, displayed here. And suppose we use some of this method, this 2-tree method, to compute the pairwise distance. So T1, T2, T3. And in this case, you look at this edge between these 2 trees, and there's a number. This number refers to the pairwise distance. So in this example, each of the any pair of the 2 trees, any pair of these the trees has pairwise distance is precisely 1. All right, and if you think about it a little bit, you will realize that the minimum reticulation for the 3 trees must be at least as large as the largest number in the pairwise distance. In this case, the largest pairwise distance is 1. In other words, the minimum reticulation for 3 trees got to be at least 1. All right. However, I want to ask this question: can the minimum reticulation for these 3 trees be precisely 1? In other words, can this lower bound be tight? And to investigate this, let's imagine we do have a network with precisely 1 reticulation events. So in this case, 1 node, and this 1 node, as I said, have 2 incoming edges. One is a red edge, one is a black edge. And so because T1 is displayed in the network, and by display I mean that I can delete one edge and keep one of the edge. Let's suppose T1 pick the red edge. Yeah. So T1. Let's suppose T1 pick the red edge, and so because T2 is also displayed in the network, and so T2. Let's suppose pick the black edge. You should realize that T2 cannot pick the same edge as a T1. Because if you pick the same edge as T1, since we only have one reticulation node, those two trees will end up being the same. But obviously, you can look at the two trees, T1 and T2 are not the same. So you cannot pick the same edge. And now the problem comes down to T3. And which edge are you going to keep to display the tree T3? And you realize that you just cannot pick either, because if you pick either, it's going to be same as either T1 and T2. So to conclude, this means that there doesn't exist any network with precisely one reticulation event display all the three trees. So the lower bound is 2, not just 1. All right. So I'm going to make this idea more precise by introducing a concept, a so-called display vector. And display vector is a binary vector which is going to represent how a tree is displayed in a given network. And this display vector has 1 bit, and for each of the reticulation event. So in other words, if you have 10 reticulation events in the network, the display vector has length of 10. All right. And the display vector will show for a given tree. So display vector is also for a particular tree, and it's going to show for each of a tree which edge you're going to choose or you're going to select to display the network. And let's first label this incoming edges onto reticulation nodes. Arbitrarily, that's 1, because we only have 2 incoming edges, so we can use a binary number. So 1 is 0, 1 is 1. So in this case, the 2 black edges coming into the reticulation node has the value 0. The 2 red edges are 1. All right. So if we think about the tree T, so the tree T has a display vector. So this is 4 edges, and the tree T will pick the 1 black edge, 0 edge, and also pick 1 red edge, yeah, which is 1 edge. So in this case, its display vector is encoded as 0, 1. All right, 0, 1. Yeah, and if you look at the tree T prime, yeah, you look at tree T prime, it will pick the different set of edges. It will going to pick the red edge, and which is a 1 edge for the first reticulation node, and it's going to pick a 0 edge and the second reticulation node. So in this case, the display vector is 1, 0. So why I'm interested in this display vector? The display vector has useful meaning when we consider the minimum reticulation. And in the sense that the display vectors cannot be too similar. And there's a simple lemma, which says the following. The Hamming distance between the display vectors for any 2 trees, T1 and T2, so which is a capital D. So the Hamming distance of display vector of T1 and T2, and got to be at least as large as a pairwise reticulation distance. So remember that I have a pairwise reticulation distance before, and this simple lemma says that this Hamming distance of a pairwise display vector cannot be too similar. All right. Okay. So this motivates the so-called RH bound. So the RH lower bound says the following: if a given number, say R reticulation events are possible, then there must exist a length K. K is the number of trees. K length R display vectors, such that it satisfies this following distance constraint. In other words, Hamming distance must be at least as large as a pairwise reticulation distance. And in analogy, this is similar to saying the following, that we want to select K points on R-dimensional binary hypercube such that these points cannot be too close. And if such key points cannot be selected, then we know that we must need at least R+1 reticulation events. And the RH lower bound is simply equal to the smallest r such that these k points can be selected on the r-dimensional binary hypercube, which satisfy this distance constraints. All right, I'll give you an example here. So here we have 3 trees, T1, T2, and T3. And in this case, we have a pairwise distance of 2, 2, 3. So distance between T1, T2 is equal to 2. And distance between T2 and T3 will be 2. And distance between T1 and T3 will be 3. And again, the minimum number must be at least 3. But the question is, can we construct a network with precisely 3 reticulation events? And this is the question I'm going to ask. And this is this 3 possible? Is 3 events possible? So in this case, we want to select 3 points from this cube, yeah, such that those points cannot be too close. So let's start with picking the display vector for T1. And without loss of generality, I'm just picking 0, 0, 0, so 3, 0 for the display vector for T1. And if you notice that this distance is equal to 3, in other words, that you must pick for T3 as 1, 1, 1. Otherwise, the Hamming distance will not satisfy the distance requirement. All right, but then you have a problem to choose the T2. Where you can place T2. And if you place, for example, here, if you pick the T2 for 1, 1, 0, you got a contradiction between T2 and T3, which the Hamming distance is 1, but the pairwise distance is 2. All right, so this is the following: the RH lower bound is 4, so the minimum reticulation must be at least 4. All right, so given all the pairwise distance of the reticulation distances, I do not have a polynomial time algorithm for computing this RH bound exactly. However, I can use integer linear programming to compute for many data, and also there is a closed form formula for the case of 3 trees. If k equals 3, and you're giving me the set of pairwise distances, I can have a closed form formula to compute this bound. All right. All right, so let me quickly go over the other side of the bounds, which is the lower bound. So in this case, the upper bound. So in this case, we want to reconstruct a network for a set of trees, T1, T2, and all the way to Tk, such that I want to use as small as possible, but it may not be the minimum. And this of reticulation events, and this number is going to provide us the upper bound, and it's also going to give us a network, true network, display each of the trees. All right, so what's the idea? The idea is that we want to sequentially inserting these gene trees, T1, T2, T3, and into a growing network, which is N. And on each step, we're going to insert in 1 tree. All right, and also to inserting a tree, I will need adding some new reticulation events so that this tree, this current tree, is displayed in the network. And to ensure that I'm not using too much of the reticulation events, I will try to minimize the number of new reticulation events on each step. So I'm not saying this is the globally minimum, but this is a minimum on each step. So here's an example. I have 3 trees, T1, T2, and T3. And let's suppose I'm going to inserting the tree in this order. And so the first network is just simply this. Yeah, we're adding 1 tree is just a tree. The network is simple as a tree, and we'll have this T2, and I'm going to adding 1 edge, also 1 reticulation node as here, and to display T2. And to see that, you can see, by following this edges, T2 is really displayed in the network. And similarly, I can adding one more event to display T3. Yeah, this is the new event, and by adding this new event, I'm going to display T3. Similarly, you can look at here, T3 is indeed displayed. So to each of a method, each of a step is is NP complete, unfortunately, but I have an integer programming to do this. And also, to get the overall bound, I'm going to try all possible ordering of T1, T2, and T all the way to Tk. And for each ordering, I compute this stepwise insertion of trees. And the overall best bound is equal to the smallest reticulation events in this network. All right. So I have a program which is Stephen mentioned, and this program I'm going to investigate how often these two bounds matches. Yeah, I said the best case is two bound upper bound and lower bound matches, and I can find the optimal. And also I'm interested in the gap. How large between the lower and upper bounds. So this shows you the percentage of data sets where the optimal solutions can be found. So we have 3 curves. Each curve corresponds to a different number of gene trees. So it's 3 gene trees, 4 gene trees, 5 gene trees. And the horizontal line shows the number of taxa. And the vertical line shows the percentage of data where the lower bound, upper bound matches. And you look in here, this case, when the number tree is small, the number of lower bound, upper bound match with a pretty high percentage, over 60% of the data matches. These two bounds matches. All right. So also about the gap, and here's again the horizontal line shows the number of taxa, and again you can see the gap for 3 trees case at least is pretty small. It's within 5% difference between these two bounds. All right. So the gap is often small. All right. So and last I will show a real example here. I have 5 gene trees. This is from real grass data set, which Stephen mentioned in his talk. And we have 5 gene trees, and I run my program, and I got a lower bound which is equal to 11, and the upper bound equal to 13. I'm not sure which one is optimal, or what is the value of an optimal number. And here is a network display each of the 5 given gene trees, and using the 13 reticulation events, and to see how is this displayed in the network. So this is one gene tree, and after you study this network for a little bit, and you realize this is how it's displayed in the network. Kind of a little bit complex. So that's all, and thanks for attention.
First question is very practical. Can you generalize this to trees on non-identical taxa sets? So you assume that all your trees have got the same set of taxa, right? Can you generalize to overlapping but not identical sets of taxa? Actually, that's
right. That's a good question. I haven't done any work on that, and because this work extends on the pairwise distance, and to compute the pairwise distance, I have to use the tree with the same set of taxa. Although you can try to merge that, and maybe there's something can be said when you have not the same set of taxa. Yeah, I haven't thought about that. That's a good question.
And you're reliant on an exact solver for 2 trees. Can you imagine lower bounds for 3 or more trees which do not explicitly use the 2-tree optima?
That's a good question. I have been thinking about it for a while, and I don't have ideas. Maybe there are some ideas using a better way to give a lower bound that is easier to be computed. Yeah, it's possible. Definitely possible.